My goal in this series of videos is to give an intuitive understanding of various topological concepts that at first might seem pretty abstract, but when they're broken down, can be seen to really come from more geometric and visual ideas from metric spaces that are perhaps somewhat more palatable. So each of these videos is going to start with a definition on the screen, in some cases a theorem, so most of the time a definition. And I'm going to make the definition as formal as possible. And then I'm going to translate that definition into English, which is honestly how most people think about them anyway. For example, when I think about this concept that I have written on the screen, I don't think about the mess of symbols that I've written. There's like an English version of this definition that I have in mind. So let's go ahead and start with this definition. So this is the definition of a topological space. Okay, so what it says here is that if you have a set X, and if you have a collection, which I'm calling tau, and it says that collection is a subset of the power set of X. Remember, the power set is just all subsets of X. So tau is really a collection of subsets of X. Then this set X together with this collection tau is called a topological space if the four properties below are satisfied. Okay, so these four properties look like they come out of the blue. Sometimes they're a bit hard to interpret when you first see them. But let me preface this by saying these four properties come directly from metric spaces. So in metric spaces, what we're used to seeing, let's say we're dealing with the real line, R, going off to infinity in either direction. What we're used to seeing is that intersections of, say, open intervals in R are actually open intervals themselves. Right, so if I draw in red the intersection, then we actually just get, oh, what do you know, another interval, right? And indeed, if you think about unions of open intervals, you still get open sets in R. Right? Maybe I had an interval here, and I had an interval here, and I had another interval, teal. Maybe this interval kind of intersected. And when I take the union of these three, or however many intervals I started with, well, the union ends up looking like those two chunks, right? But it's still an open set in the sense of the real line as a typical metric space. Hopefully you agree with that. It's not an open interval, but it's an open set. Okay, so the rules here, particularly rules 3 and 4, just outline those two properties. So ignoring the first and second rule, the third rule says finite intersections of open sets are open. And you're probably thinking, whoa, how did you interpret it that way? It looks very different to my eyes. And here's the next part of the definition. Elements of tau, remember tau is this collection of subsets. So elements of tau are referred to as open sets. Okay, so in that metric space example, those intervals would have been elements of tau. They're open intervals. And what this thing really says is that if you give me two open sets, keep in mind, element of tau just means open set. So U1 and U2 are open sets. Then their intersection has to be an open set as well. And so maybe you're thinking, okay, you should have written the intersection of two open sets is open. But they're equivalent, right? You could extend this thing by induction. So if you start off knowing that the intersection of two open sets is open, you can inductively argue that the intersection of any finite number of open sets is open. And vice versa, if you know that all finite intersections of open sets are open, you know that the intersection of two open sets will be open. So anyway, that's just outlining what we got from metric spaces, how two open intervals intersected to give another open interval. And property 4 does something similar, except it does it not in the finite case, but in the arbitrary case. It means you can union together as many open sets as you want, and you'll still get an open set. So I'll say arbitrary unions of open sets are open. There you go. So those are the two important properties. The remaining two are just things that you just need them, otherwise like the other two properties fall apart. So for example, like if we were thinking of the real number line, the whole thing is considered an open set. You don't often talk about that in analysis or calculus or anything, but yeah, it's important to say the whole space is open, just by definition. And sort of vacuously, the empty set is open. And if you think back to what a metric space is, or what an open set in a metric space is, then you think, okay, an open set in a metric space is the set of all points for which you can kind of like fit a neighborhood inside that set. The open set vacuously fulfills that criteria because there are no elements in the empty set, so it fulfills any criteria, really. You can say anything you want about the empty set and it's going to be true. So we make it an open set just so things don't fall apart. In particular, if you look at, say, condition 3, if you had two disjoint open sets, their intersection would be empty, and you still want that to be an open set. So if you threw out condition 2, things would be bad for condition 3. Anyway, those 4 properties come from metric spaces, right? They're true for any metric space you design. And so by definition, we want them to be true for topological spaces. Now, that set tau that I was mentioning is called a topology on the set X. We never say the topology, it's always a topology, because the topology is not unique. You could define a bunch of topologies on your set X. You know, depending on how big X is, you could take a bunch of different subsets with these 4 properties and generate a totally different topology. So yeah, we use a instead of the. But the reason we require these 4 things to be true is because a topological space is sort of like a metric space without a metric. As weird as that sounds. But these 4 properties ensure that even though you don't have a metric, you don't have a notion of distance, you still have some way to recover, to like use the definition of open here to recover some notion of closeness. And we'll see that a bit more when we get to the discrete and indiscrete topologies, one of which you're like really good at telling points apart, and one of which you can't tell points apart. That won't make sense until I define what those concepts are. Anyway, for the time being, think about a topological space as a metric space without a metric. And trust me that it turns out to be incredibly useful. So what are some examples of topological spaces? Well, the first example, any metric space, right? I just mentioned that metric spaces work. So if you give me a set X and you give me some metric D, then the metric space, which we typically write as a tuple X comma D, is a topological space in its own right. You can think of the open sets of the topology as arbitrary unions of open balls. And that's how it works in the Euclidean topology or the Euclidean metric space. In that, if you consider X to be the real line, then, well, these are sort of two ways of phrasing the same thing. It's something you know from analysis, that a set is open in Euclidean space if it can be decomposed into a countable union of open intervals. Right? No matter what open set you draw in R, it's always going to be some union of these things. That one is kind of interesting, kind of tough to prove. And so you say, if you want to go in reverse, you say that the open intervals generate the topology, the Euclidean topology. And indeed, no matter what metric space you're given, well, with a metric space, you get open balls, and those open balls generate the metric topology, which is the topology associated with that metric space. Anyway, all that goes to say, every metric space is automatically a topological space. In particular, for the real line with Euclidean topology, these are your open intervals, and they generate all possible open sets. So take intersections, take unions of these, you'll get everything you need. So that's maybe not surprising. One potentially surprising thing is that's not the only topology you can put on R, right? I said topologies aren't unique. What if you define a topology like this, where instead of just any open intervals, you only take the right pointing open rays. So for example, this is the real line, and I could take the open ray from 1 to infinity. That's an open set. Again, keep in mind, tau is the collection of all open sets. Everything in tau is an open set, and every open set is in tau. There are no open sets that aren't listed. It's like an exhaustive list of all open sets. So yeah, 1 to infinity, that's an open set. And why is that a topology? Well, it's a topology because if I took the intersection between, that open set and 0 to infinity, what's their intersection going to be? Well, their intersection is the yellow one, which is an open set. What's their union? The union's the purple one. And it turns out, even if you union a bunch more purple things on here, and maybe they approach some limit or something, that's still going to be an open ray from, I guess you could say, the infimum of their left endpoints to infinity. Okay. Yeah, and I guess I forgot something, which I'll write now. Hopefully you caught this. We forgot, or I forgot. Always got to include the empty set and the whole space. But there you go. Right. Easy peasy. So that's one weird topology you can define. What if you're not working on the real number line? What if you want to work with, say, some finite set? Here's a finite set, just the collection ABC. So I've just put a few points down here in the space X. And I've defined what I'm claiming is a topology. Okay, it's a collection of subsets. These are the things I'm calling open, but the word open starts to lose its meaning when you get into weird topologies like this. Anyway, let's draw what the open sets are. The empty set's open. So I'll just put that out in nowhere land because it's kind of hard to draw the empty set as anything other than that symbol. The set AB is an open set. So basically, I'm going to draw my open sets in blue. BC is an open set. And The singleton just containing B is also an open set. Finally, the whole space is an open set, so let's just put a big blue circle around everything. And those are the only open sets, right? There are 5 of them. 2 of them have to be there, the empty set and the whole space. The others I kind of chose so that they would fulfill the properties we needed them to fulfill. Namely, this blue set intersected with this blue set gives me what? Well, it gives me this blue set. And you can go through and exhaustively check, no matter what 2 blue sets you pick, their intersection is going to be another blue set. And here I'm just using blue set to replace open set. Similarly, if I took unions, nothing would change. I would still get blue sets. So unions of blue are blue. The empty set is blue. The whole space is blue. So everything I need to be open is open, basically. And you could do a lot of other topologies on here. But not every collection of subsets will be a topology. So for example, this one. If I take just A and B, so let's erase what I just drew. So I'll keep these 2 in here because they trivially have to be open sets. So empty set and whole space are declared to be open. And then what if I say, okay, the singleton A and the singleton B are open? Is that good enough to give me a topology? The answer is no. Why? Well, the union of A and B would have to be an open set, but it's not listed. We're missing the set containing A and B, which is the union of these 2 things. So rule 4 said arbitrary unions of open sets have to be open. I declared these to be open. That means this one has to be open, but it's not, right? It wasn't listed in the topology. So that collection is not a topology. And again, you might be thinking, okay, it seems arbitrary. Why those 4 properties? Pretty much exclusively because they mimic metric spaces. So something like this would not be able to generate a metric space. And metric spaces are nice, so we like to mimic them whenever we can. Cool. So that's our intro to topological spaces. Next, we'll talk about what it means for sets to be closed, or both closed and open, or neither. And from there, we'll start developing some more advanced concepts. Thanks for watching.